where wonder lingers like mist over still water, and science strolls gently through the pages of deep time. Tonight we're curling up with one of the most enduring mysteries of all, a question that has echoed softly across centuries, tucked into old books, whispered through microscopes, and carried on the breath of stardust. How did life begin on Earth? Not just cities and songbirds and sunflowers, but life itself. The first spark, the first flicker, the moment when chemistry became biology and stone gave rise to story. Wherever you are listening from, a quiet corner of your bedroom, the hum of a night train, or wrapped in a blanket of stars on the other side of the world, I wonder, how alive does your world feel tonight? Is there a tree outside your window? A breath of wind? Maybe just the slow rhythm of your own heart, still beating after 4 billion years of evolution have brought it here. If this gentle journey brings you peace, if you find comfort in questions without simple answers, or if you're just looking for a softer way to drift off, I'd be ever so grateful if you liked the video, maybe subscribed, and help this cozy corner of curiosity reach others wandering the night. So settle in, slow your thoughts, let your breath match the rhythm of the earth below you, and let's begin. Because somewhere, in the warm, shallow silence of an ancient ocean, among minerals and molecules and sunlight sifting through waves, something remarkable happened. Something utterly ordinary, and yet the beginning of everything, life. Not as we know it now, with bones and brains and books, but as it once was, fragile, formless, microscopic, a whisper against the roar of geological time. Roughly 4 billion years ago, on a planet still young and often violent, something stirred. Not all at once, not in a single flash, but slowly, gradually. A quiet kind of magic. Not the breaking of rules, but the patient unfolding of them. From chaos, chemistry. From chemistry, cells. But how? And why here? On this blue-green planet orbiting an average star in a quiet corner of a spiral galaxy? And perhaps most mysterious of all, how did life survive? Sometimes the past begins not in dusty fossils or distant deserts, but in the faintest of present-day puzzles. Take, for instance, a strange rock pulled from the western shores of Greenland, a place where the Earth wears its age on its sleeve. It was there, in the 1970s, that geologists discovered what seemed to be just another streak of banded iron, rippling with crimson and grey. But under the scrutiny of scientists like William Schopf and Stanley Tyler, that ordinary-looking stone began to hum with something extraordinary. Microscopic patterns, curved and clustered, not quite random. They looked suspiciously like fossils, not dinosaur bones or trilobite shells, but far older, more delicate, tiny threads, barely distinguishable from the rock itself, yet possibly alive over 3.5 billion years ago. Elsewhere, across the ocean and half a world away, a different clue emerged. Deep beneath the simmering surface of the ocean, where tectonic plates crack open like slowly torn pages, there are places called hydrothermal vents, chasms that breathe heat and chemicals into the icy blackness. When the Alvin submersible first descended into those abyssal plains in 1977, no one expected to find anything living. And yet, there they were, clusters of life thriving in darkness, tube worms, blind shrimp, whole ecosystems powered not by sunlight, but by chemistry. It was like stumbling into another planet, a world within our world, and with it came a question no longer easy to ignore. If life could begin here, in heat and pressure, with no light at all, then maybe our ideas about life's origins needed rethinking. A compass needle twitching in the wrong direction, a rock whispering secrets, a creature thriving where nothing should. These are the moments where the present becomes a map to the ancient. Scientists like Jack Szostak, Gerald Joyce and Adi Nath have spent decades listening to those whispers, piecing together a mystery not with certainty, but with quiet persistence. Not a single answer, but a mosaic of overlapping clues. And perhaps the most humbling part is this. We don't have fossils from the very beginning. Life in its earliest form left barely a trace. What we do have is chemical memory, isotopes tucked into ancient rocks, molecular patterns that hint at processes long since faded from view. They're not shouting, these signals. They're barely audible. But when you string them together, they begin to tell a story. One that starts not with life, but with a planet still becoming itself. The Earth, when it was young, was not a welcoming host. Picture a sky without blue, no breathable air, no trees, no bird song, the surface boiled with volcanoes, the oceans thick with minerals, the land, what little existed, battered by asteroids and bathed in ultraviolet radiation. And yet, this chaos created opportunity. It was a world rich in ingredients: hydrogen, methane, ammonia, water, energy from lightning, from solar rays, from the very heat rising from the planet's molten core. In the 1950s, two researchers, Stanley Miller and Harold Urey, tried to mimic those ancient conditions in a flask. They filled it with gases thought to resemble early Earth's atmosphere, then sparked it with simulated lightning. Days later, the flask had changed. It now contained amino acids, the very building blocks of proteins, and by extension of life. It wasn't life itself, but it was a whisper of possibility. From there, a new kind of exploration began. Not of stars or galaxies, but of molecules. Scientists began to ask, could simple compounds become complex ones? Could molecules fold into machines? Could chance interactions become organized, then self-sustaining, then alive? The question of life's origin isn't a single question. It's a chain of them, a slow burn, not a spark. And each link is being uncovered by researchers not just in labs, but in caves, deserts, deep-sea submersibles, and even on Mars. In South Africa, microbial mats preserved in ancient rocks tell of bacterial colonies that once bloomed across tidal flats. In Australia, stromatolites, layered structures built by ancient microbes, still grow in shallow lagoons, echoing a process billions of years old. These are not fossils in the traditional sense. They are fossils of behaviour, evidence not just that life existed, but that it organised, collaborated, built. And then there's the chemistry written into our own cells. Inside you, right now, are structures called ribosomes, tiny factories that translate genetic code into proteins. They're ancient. So ancient, in fact, that their structure barely varies across all known life. It's like stumbling upon the blueprint of an original machine, still in use after billions of years. Ada Yonath, who helped reveal their structure in astonishing detail, once described them as molecular fossils, preserved not in stone, but in function. The more we learn, the more remarkable it becomes that life began at all. The leap from simple molecules to something that can copy itself, protect itself, adapt and persist. It's like asking a handful of pebbles to organise into a pocket watch, and yet, on Earth, it happened. Not once, perhaps, but many times. False starts, partial attempts, tiny bursts of chemistry that fizzled out, until one, somehow, didn't. The first life was likely simple. No nucleus, no mitochondria, no organised organs or limbs. Just a membrane, a handful of genes, perhaps floating in a droplet of water. But it was enough. Because from there, evolution took hold. Mutation, variation, selection. The same processes that shape coral reefs and crow songs today were already at work in those ancient pools, nudging life forward molecule by molecule. Where exactly did it begin? That's still a matter of debate. Some favour deep sea vents, where minerals and heat provide the perfect Petri dish. Others look to shallow coastal lagoons, where evaporation concentrates ingredients and sunlight offers energy. Still others suggest that life may have formed not on Earth at all, but arrived via meteorite, not alien in the sci-fi sense, but cosmic in origin. We know that some meteorites contain amino acids. We know that organic molecules exist in interstellar clouds. The building blocks of life are not rare. What's rare, perhaps, is the container, a planet just stable enough, just wet enough, just long-lived enough to let the story unfold. We may never find the precise location of life's cradle. It could be lost, subducted into the mantle, erased by time. But we can trace its fingerprints, in carbon ratios, in molecular patterns, in the quiet persistence of microbes who still live in boiling springs and acidic lakes, just as they did billions of years ago. And that's the wonder, that life, once begun, refused to stop. Even when the Earth froze over in global ice ages, even when oxygen nearly wiped everything out, even when fire rained from the sky, life adapted, hid, collaborated. It built itself into new forms over and over. So when we study rocks and oceans and genes, we're not just uncovering ancient history, we're listening to a survival story still in progress. And all of it, every leaf, every lung, every laugh, began with that first improbable flicker. Not in grandeur, not in thunder, but in quiet repetition, a molecule that copied itself. Then again. The beginning wasn't a moment, it was a momentum, and it's still going. Imagine standing at the edge of a shoreline, but not one you'd recognize. No palm trees, no shells, no seagulls circling above. The sun is faint and ruddy through a dense toxic haze. The air is thick with gases that would make you cough in an instant. Methane, hydrogen sulfide, ammonia, the breath of a planet still forming its lungs. The oceans stretch endlessly, green-black and restless, laced with iron and stirred by tides that pull harder than they do today. The moon is closer, looming huge and bright in the sky, its gravitational grip yanking the seas into massive daily swells. This is Earth, not as a cradle of life, but as an untamed forge. A place still cooling from its creation, where continents have not yet settled, and the ground itself trembles with each new addition to the planetary crust. Volcanic arcs bloom and like scars across the ocean floor. Asteroids still fall from space, now and then, not as gentle shooting stars but as cataclysmic intrusions, reshaping coastlines in an instant. There is no soil yet, no grass, no rustling leaves. The land, where it exists, is barren, jagged, and dark. Basaltic rock, slick with rain and minerals, steams under the pale sun. And yet, in this volatile chaos, there is a quiet rhythm forming. The oceans bubble with possibility. Not metaphorically, quite literally. Deep beneath the surface, where cracks in the Earth's crust leak scalding water rich in minerals, tiny pockets of energy are forming microcosms. The temperature gradients, the chemical gradients, the simple but relentless interactions between metal and molecule, all of them dance to a kind of music. This may be where the story begins. Hydrothermal vents, some shaped like chimneys, others like shimmering fields of metal and stone, act as crucibles for early chemistry. In their proximity, the boundaries between geology and biology blur. Minerals like iron and nickel become catalysts, coaxing carbon atoms into new arrangements. Fatty acids, floating in the broth, spontaneously form bubbles, membranes, capable of surrounding themselves and holding a bit of order in the chaos. These primitive enclosures aren't alive, not yet, but they are a start. Elsewhere, in sunlit pools near the edge of volcanic islands, ultraviolet light penetrates the surface and dances with hydrogen cyanide, forming complex organic molecules. Rainfall brings in more ingredients. Tides churn the contents. Evaporation concentrates them. These cycles, heating, cooling, drying, soaking, act as nature's laboratory. And though it may take hundreds of thousands of years for any noticeable progress to be made, Time is not in a hurry. The ancient Earth is patient. The atmosphere is unrecognisable by modern standards. It's thick with carbon dioxide, with no free oxygen to speak of. This absence is not a flaw, it's a feature. Life, as we know it, cannot yet breathe. But simple molecules, carbon-based chains, nucleotides, amino acids, thrive in this anoxic world. The sky is orange and murky, more Mars than Earth, tinged with the gases released by constant volcanic activity. Lightning forks through the clouds, not as a passing storm, but as a regular feature of the landscape. Each bolt, each surge of energy, is another chance for molecules to rearrange, to experiment. Down in the oceans, beneath the waves, the water itself is different. Rich in dissolved metals and chemicals, it acts less like a passive solvent and more like a collaborator. Iron flows freely, not yet rusted by oxygen. Silica, sulfur and phosphorus move between thermal vents and rock formations, and somewhere in these mineral-soaked shallows, the first strands of something resembling RNA begin to form. RNA, ribonucleic acid, is a molecule capable of both storing information and catalyzing reactions. In a world without proteins or DNA, this double-duty molecule could have been the first bridge between non-life and life. Some strands replicate imperfectly, introducing variation. Some fold into useful shapes, some persist. Again, this is not a moment. It's not a spark. It's more like a long and intricate dance between possibility and entropy. Molecules collide, fail, reform, try again. And over time, certain patterns begin to outlast others. Tiny protocells, bubbles with genetic-like material inside, start to emerge. They're fragile, vulnerable, but in the right environments, they find stability. And stability in a chaotic world is everything. In the warm brine of a tidal pool or clinging to the mineral-rich slopes of a hydrothermal mound, the first cells may have finally taken hold. Not complex organisms, not yet even bacteria as we know them, but structures capable of growing, dividing and evolving. Cells with membranes made of simple lipids. Cells with strands of RNA guiding rudimentary metabolism. Cells that could respond, faintly, primitively, to their environment. From here, the planet begins to change, not overnight, not even in a single era. But the moment biology enters the scene, Earth becomes a different kind of world. These early cells are anaerobic, they do not need oxygen. Instead, they rely on chemical gradients. They harvest energy from hydrogen, sulfur, iron. They adapt to extremes. Some hug the edges of volcanic seeps. Others float in the upper layers of the ocean, drifting with currents, gathering what sunlight they can. Photosynthesis, the process of turning sunlight into energy, doesn't appear right away. But eventually a new class of microbe evolves a trick so powerful it will alter the entire planet. The ability to split water using light, releasing oxygen as a byproduct. These are the ancestors of Cyanobacteria, and with them comes a slow revolution. The Great Oxygenation event, as it's now called, was not a sudden flood of air. It was a gradual poisoning, at least from the perspective of the life that came before. Oxygen, while crucial to modern organisms, is a reactive and dangerous gas. To those first microbes, it was lethal. Mass extinctions followed, but so did opportunity. For those that survived, oxygen opened new doors. Metabolisms became more efficient. Energy could be harvested in larger amounts. And new cellular structures began to evolve. Internal compartments, membranes, complexity. Eukaryotes, cells with nuclei, some were born. But that's still a long way off. In this ancient world, we are still with the earliest pioneers. Microbes that leave no bones, no teeth, but who leave behind clues. Layered mats of sediment built by colonies of cyanobacteria begin to dot the shallow seas. These stromatolites, some of which still form today, are living monuments to a time when all life was microbial and every inch of progress was won over millions of years. The Earth, meanwhile, continues its own transformation. The crust cools and thickens. The first proto-continents emerge. Weather begins to shape the landscape. Rain falls on land for the first time, carving rivers, forming lakes. And through it all, life holds on. Minute, unseen, but tenacious. We know these things not from guesswork, but from the rocks beneath our feet. Zircons from Western Australia, over 4 billion years old, contain traces of early oceans. Isotope signatures tell us when oxygen began to accumulate. Microfossils, though rare and debated, hint at biological activity dating back at least 3.5 billion years. These are not smoking guns. They are brushstrokes on a vast and ancient canvas. Even in the face of uncertainty, patterns emerge. Simplicity giving way to complexity. Chaos giving way to structure. Life growing not in spite of the Earth's violence, but because of it. The ingredients were everywhere. The conditions, harsh but rich. The planet was a paradox, dangerous and nurturing, chaotic and fertile. And in that paradox, life found its foothold. As we trace these earliest eons, it becomes clear that life is not an accident. Nor is it inevitable. It is something in between, a probability stretched over a long enough timeline, a result of the universe's laws rendered through trial and error over eons. In the stillness of a deep-sea vent, in the warmth of a sunlit pool, in the quiet assembly of lipids and nucleotides, the Earth made a bet. That order could rise from disorder, that memory could emerge from chemistry, that something could begin, and it did. If the origin of life was a whisper, then what followed was a long crescendo, a symphony of change, triggered not by intent but by the relentless rhythm of chemistry unfolding across a restless Earth. There is something elegant in the idea that life, in its earliest days, was shaped by the same forces that shape mountains and storms, not apart from the planet, but an extension of it. And yet, for all its quiet beginnings, the chemistry of life does not stay quiet for long. Once those first cells, simple, membrane-bound, perhaps capable of replication, took hold, they faced a new and subtle challenge: survival through variation. To stay alive in a volatile world, life would need more than just resilience. It needed adaptability. And that required change in structure, change in function, change written into the molecules themselves. The first major transformation may have come in the form of metabolism, the ability to harvest energy from the world around you and turn it into fuel. Some early cells did this using sulfur, others iron, still others hydrogen. But eventually a new strategy emerged: capturing light. Photosynthesis, not quite the kind we know today but a primitive form, allowed certain cells to tap into sunlight, splitting molecules like hydrogen sulfide to generate energy. These were the ancestors of modern phototrophs, and though they left few direct fossils, they left behind patterns, chemical shadows, that suggest their presence as far back as 3.4 billion years ago. But then came the real shift: a mutation, a leap, or perhaps a slow drift over generations. We may never know. But at some point, one lineage of microbes developed the ability to split water molecules, not sulfur. This was a monumental change. Water, unlike hydrogen sulfide, is everywhere, but splitting it apart is harder. It takes more energy, it's more dangerous, because it releases something toxic: oxygen. To us, oxygen is life. We breathe it, we depend on it. But to early life, oxygen was a threat, a reactive, corrosive molecule that damaged proteins and scrambled genetic material. When the first oxygen-producing organisms, likely cyanobacteria, began releasing it into the oceans, they were unknowingly setting the stage for both catastrophe and transformation. At first, the oxygen didn't build up in the atmosphere. It reacted with the iron in the oceans, forming vast deposits of rust, iron oxides that settled onto the seafloor in rippling bands. These banded iron formations still exist today, striking red and grey rocks that record a time when the planet was digesting the byproducts of its own innovation. But over time, the sinks filled up. The oxygen had nowhere else to go, and so it began to leak into the air. The Great Oxygenation event around 2.4 billion years ago wasn't sudden. It took millions of years, but its impact was profound. For the first time, Earth's atmosphere began to shift. Methane levels dropped. Greenhouse warming weakened. The planet may have plunged into ice ages, even what some call Snowball Earth, where glaciers reached the equator, and many of the anaerobic organisms, those that had flourished in oxygen-free environments, began to die out. This was Earth's first mass extinction, not caused by fire or impact, but by a molecule, by a change in the chemistry of the sky. But as always, life adapted. Some microbes evolved defences, enzymes that could neutralise oxygen's harmful effects. Others went further, developing new ways to use oxygen, turning a deadly gas into a powerful tool. Aerobic respiration, the process you and I use to turn food into energy, is far more efficient than anaerobic methods. It produces more ATP, the energy currency of cells, for every molecule of sugar consumed. This was evolution's version of upgrading from a campfire to a furnace. And with more energy came more possibilities. Cells could grow larger. They could support more complex internal machinery. They could afford to specialise. It is in this period, not long after the oxygen crisis, that we begin to see signs of a new kind of cell, the eukaryote. These were the first cells with internal compartments, with nuclei to house DNA, with organelles to manage energy and waste. And while we don't know the exact details of how they evolved, one theory stands out as both elegant and bold: endosymbiosis. Imagine a smaller bacterium, perhaps an ancestor of the modern mitochondrion, drifting into the interior of a larger host cell, not as an invader, but as a partner. One provided energy, the other protection. Over time, they became inseparable. The smaller cell gave up its independence, its genes merged with the host, and a new kind of organism was born. This wasn't just cooperation, it was integration. Later, a similar merger may have occurred again, this time with a photosynthetic bacterium, the ancestor of chloroplasts, the green engines of plants. Once more, life absorbed life, and the blueprint for complexity was refined. With eukaryotes, the pace of biological innovation accelerated. Cells became more efficient, they communicated, they formed colonies. Some began to specialise. One cell for movement, another for feeding, another for reproduction. These were the first steps toward multicellularity, but Earth wasn't done testing them. Around 700 million years ago, the planet entered another deep freeze. Glaciers once again wrapped the globe. Whether triggered by changes in atmospheric carbon or shifts in continental positions, the result was the same. Life retreated to the edges, to warm pockets near hydrothermal vents, or perhaps beneath insulating layers of ice, but it survived. Again. And when the ice finally melted, when the ocean stirred back to life, evolution had new room to play. Oxygen levels rose higher than ever before. Nutrients washed into the sea. Genetic complexity reached a tipping point. And soon after came the Cambrian explosion, a burst of innovation, of arms and eyes and armour, a world alive with motion. But that's still far ahead. For now, we remain in the realm of single-celled pioneers, chemists of the early biosphere, survivors of catastrophe. We study them not through bones, but through clues, isotopes in ancient rocks, molecular fossils, bits of lipids that resist decay, genetic sequences conserved across billions of years, whispering of ancient partnerships and quiet revolutions. These early changes, oxygenation, endosymbiosis, internal compartmentalization, were not immediate. Each took millions of years. Each involved countless failures, but each was a doorway, a mechanism of change, not a single leap, a staircase. A staircase, then, one step after another, shaped not by a grand design but by 1,000 quiet adjustments to the rules of survival. A game played over geological time with no end goal, only continuity. To live, and then, if possible, to live better. And so life climbed, even as Earth itself trembled and shifted beneath it. Around 2.1 billion years ago, in the shallow seas of what is now Gabon in West Africa, life took another tentative step. Preserved in the mudstones of that ancient coast are fossils of what some scientists believe to be the earliest examples of multicellular organisms, flat quilt-like bodies arranged in orderly patterns. Not just clumps of cells, but coordinated structures. Organisms that show polarity, organisation, growth. Signs that cells were no longer simply duplicating, but cooperating. This was not multicellularity as we know it in jellyfish or oak trees, but it was a start. The biological equivalent of villages forming from a scattering of tents. Why did it happen then? One theory points again to oxygen. As levels rose, the energy budget of living cells expanded. Metabolisms became more powerful, complex tasks could be delegated, and when cells discovered that sticking together offered more advantages than going it alone, protection, efficiency, even division of labour, evolution favoured those who stayed united. Still, progress was slow. For hundreds of millions of years, life remained mostly microbial. Algae floated in the oceans. Mats of bacteria-coated rocks. Stromatolites dotted the coast like biological coral reefs. They were the engineers of their age, oxygenating the planet, cycling carbon and nitrogen, setting the stage for all that would follow. And then, around 800 million years ago, something stirred again. A cascade of tectonic events reshaped the continents, creating new coastlines, altering ocean circulation, and perhaps shifting the balance of nutrients in the sea. Phosphorus, long scarce, became more available, a crucial ingredient for DNA and cell membranes. The engine of evolution sputtered, then surged. Life, once confined to single cells, began to assemble itself in new and astonishing ways. The first animals, soft-bodied, strange, alien, appeared in shallow waters. They left behind impressions in the rock. Dickinsonia, with its ribbed, pillow-like form, Charniodiscus, shaped like a frond but clearly not a plant. These ediacaran creatures were neither fish nor fungi, neither insects nor plants. They were their own thing, evolutionary experiments drifting in warm seas, and even here, oxygen played a role. It allowed organisms to grow larger, to support more tissue, to develop nervous systems and muscles. It enabled movement, a radical innovation. For the first time, life wasn't just drifting. It could swim, it could crawl, it could chase or flee or choose. And with movement came interaction. Predator and prey, competition and cooperation. Evolution, once slow and meandering, began to pick up speed. This feedback loop, energy allowing for complexity, complexity driving competition, competition refining form and function, would become the central engine of biological innovation. And it all began with those early chemical shifts, those tiny molecular changes that allowed oxygen to enter the game. But oxygen wasn't the only actor. The Earth itself kept shaping the script. Massive volcanic eruptions periodically clouded the skies, releasing sulfur and ash. One such event, known as the Uram excursion, altered the global carbon cycle so dramatically that it left a chemical fingerprint in rocks across the world. Methane ebbed and flowed in the atmosphere. Ocean chemistry shifted. Ice advanced and retreated. And through it all, life adjusted. Some researchers believe that these environmental upheavals didn't just threaten life. They accelerated its creativity. Bottlenecks forced innovation. Harsh climates selected for resilience. The line between extinction and adaptation narrowed. sharpening the edge of natural selection. Around this time, in the microbial world, something else remarkable occurred: sex, or more precisely, genetic recombination. Instead of reproducing by simple division, one cell becoming two identical copies, some eukaryotes developed a method of exchanging genetic material, mixing DNA from different parents to create something new. The implications were enormous. Variation is the raw material of evolution, and sex, by shuffling the genetic deck, produced a flood of variation. New combinations, new traits, new potentials. Evolution, once a slow river, became a winding, rapid stream. It's hard to overstate how fundamental these changes were. Endosymbiosis, oxygen metabolism, multicellularity, sexual reproduction. Each was a revolution and each built upon the last. And perhaps most striking of all, none of them were inevitable. In the grand scheme of the cosmos, there's no rule that says life must evolve complexity, that cells must form communities, that mitochondria must emerge, or that DNA must spiral into its elegant helix. These were outcomes shaped by context, chance, and chemistry, guided by the invisible hand of selection, but never promised. Even here on Earth, complexity was delayed many times. False starts, global setbacks. The rise of oxygen might have snuffed life out altogether. Ice ages might have frozen its chances. Volcanism might have stripped the atmosphere bare. And yet, life persisted, like a flame that refuses to die out, flickering, dimming, then flaring again. We see that persistence not just in fossils but in living relics, extremophils that thrive in boiling vents or acidic lakes, archaea that flourish in salty brines, bacteria that feed on radioactive minerals, quietly multiplying in places no other life would dare. They are not echoes of ancient life. They are ancient life, direct descendants of the earliest forms, still wearing the biochemical badges of a bygone Earth. In their DNA we find hints of ancestral genes. In their metabolisms we glimpse strategies billions of years old. And in their survival we see a kind of time machine, life, unbroken, stretching back to a moment when the Earth was only just becoming recognisable. All of this, every adaptation, every mutation, every twist in the double helix, was the result of change. Triggered not by intent but by imbalance, a new chemical, a shift in the sea, a tectonic crack letting in just a bit more heat or metal or light. Change is the sculptor. Life is the clay. And sometimes the sculptor is dramatic, an asteroid, a flood basalt, a supernova. But more often, it is subtle. The slow oxidation of an ocean, the migration of a gene, the rearrangement of a lipid in a membrane. These are the mechanisms of change. Tiny, cumulative, profound. They do not happen in silence exactly. But their music is slow, their rhythm is patient. So when we look at a tree, or a starfish, or the lines on our own palms, we are not seeing the product of design. We are seeing the trace of millions of quiet decisions, of molecules bumping in warm water, of cells dividing under a ruddy sun, of crises met and overcome again and again. And that is the miracle. Not that life emerged, but that it changed, that it continued. From carbon and sunlight, from water and rock, from the breathless air of a planet not yet ready to host a biosphere. Life found a way. Then another still. And those ways became habits, and those habits became patterns. And those patterns, eventually, became us. So when we ask, how did life begin? The answer is this. It began with chemistry, but it continued through change, and that, more than origin, is the real story. Once change begins, it rarely stops. It spills forward, nudging, toppling, and reshaping everything it touches. Not all at once, and not always cleanly, but with the slow insistence of water carving a canyon. What began as a spark in warm ancient oceans became a rising tide of interactions, of consequences. Life, it turns out, is not just a passenger on this planet, it is a participant, and eventually it became an architect. We've already seen how the rise of oxygen reshaped the world, a single metabolic innovation that turned a toxic byproduct into a global atmospheric shift. But that was just the overture. The real story lies in the countless reactions that followed, in what oxygen did to the oceans, the rocks, the climate, and every living thing that dared breathe. As oxygen began to accumulate in the atmosphere, it altered the chemistry of the entire planet. Elements behaved differently. Iron, once freely dissolved in seawater, began to rust out, settling to the seafloor in thick bands. Sulfur, nitrogen, and carbon all entered new cycles, governed by new redox conditions. The oceans themselves changed colour, from greenish and murky to clearer, bluer, but more stratified. Surface waters became oxygen-rich. Deeper layers, deprived of mixing, grew stagnant and anoxic. These layers formed invisible boundaries, habitats stacked in vertical tiers, and life adapted accordingly. Some microbes clung to the surface, basking in the light. Others lingered below, feasting on sulfur and methane, thriving in the shadows of ancient chemistry. Some species began to specialize in transition zones, where gradients met and energy could be harvested from contrast. Meanwhile, on land, still barren, still lifeless, the wind and rain slowly eroded rocks, carrying minerals into the sea. Phosphorus, washed from fresh rock, fueled microbial blooms. This, in turn, drew down carbon dioxide from the atmosphere, weakening the greenhouse effect and nudging the climate into another icy episode. Over and over, feedback loops like these sculpted Earth's biosphere. Life influenced the planet reshaped life, and so it continued. Each innovation led to ripple effects, some constructive, others catastrophic. When early eukaryotes began to spread, they changed how ecosystems worked. Their larger size made them better competitors. Their organelles allowed them to process energy more efficiently. Their sexual reproduction introduced diversity that bacteria could only dream of. And with diversity came unpredictability, new forms, new metabolisms, new interactions. Predation emerged, the act of one cell engulfing and consuming another not as a mistake, but as a strategy. For the first time, survival wasn't just about tolerating the environment, it was about surviving each other. Imagine that shift, a world where life was passive, and then one where life began to hunt. These early predators didn't have teeth or claws, but they had speed, mobility, chemical sensors. Some extended pseudopods, false feet, to trap and engulf their prey. Others evolved toxins to disable their targets. And as prey adapted, predators did too. An arms race had begun, slow but inevitable. The pressures of competition pushed organisms toward specialization. Some grew protective shells, others developed internal skeletons made of silica or calcium, and the chemistry of the oceans shifted again to support them. When calcium carbonate precipitated from seawater, it provided building material for the first reefs. These weren't coral reefs as we know them, but microbial mounds, stromatolites and thrombolites, layered structures built by communities of bacteria. Each layer represented a day, a tide, a rhythm. These formations were both homes and machines, cycling nutrients, buffering acidity, creating microhabitats. Life, which had once been dispersed, began to gather. Colonies formed, communities emerged, and in these early ecosystems cooperation flourished. Some microbes produced oxygen, others consumed it, some fixed nitrogen, others broke down waste. These interdependencies created resilience, a kind of biological insurance against environmental change. It also marked the beginning of ecosystems, complex networks of organisms and chemistry, working in tandem, maintaining balance through their very entanglement. But balance is not stasis. With each new relationship came the potential for collapse, Oxygen, for all its power, is volatile. Too much of it can ignite wildfires. Too little, and aerobic life suffocates. The carbon cycle, delicately managed by photosynthesis and respiration, is sensitive to change. A surge of volcanic activity can release enough CO2 to warm the planet. A wave of photosynthetic blooms can bury it, cooling things down. And sometimes, those cycles spun out of control. The late Proterozoic eon, spanning from about 1 billion to 541 million years ago, was marked by extremes. Glaciations blanketed the Earth in ice not once, but possibly twice. These Snowball Earth events were among the most severe climate disruptions in planetary history. Glaciers may have reached sea level near the equator. Oceans may have frozen over, trapping heat beneath miles of ice. For tens of millions of years, the planet lay dormant, white and still. But even in that stillness, life endured. Hydrothermal vents provided heat. Volcanic islands may have created oases. Some scientists speculate that thin belts of open water, slushable zones, persisted near the equator, allowing photosynthesis to continue in narrow bands. Others point to evidence of microbial mats and cyst-forming algae, capable of hibernating through long, dark winters of the globe. When the Earth finally thawed, thanks perhaps to volcanic carbon dioxide accumulating in the atmosphere, the meltwater brought nutrients. Phosphorus surged into the oceans, sunlight returned to the surface, and life, long dormant, bloomed once more. This resurgence set the stage for one of evolution's most dynamic chapters. In the Ediacaran period that followed, complex organisms began to appear in greater numbers and diversity. Soft-bodied creatures drifted and crawled across the seafloor. Some stood rooted in place like stalks. Others moved slowly, grazing microbial carpets. A few bore symmetry, radial or bilateral, early hints at the body plans that would one day produce spines, shells, eyes. These organisms didn't just represent new biology, they represented new behaviours, movement, sensing, response. With them came new ecological roles: filter feeders, detritivores, grazers, burrowers. These activities reshaped the seafloor, mixing sediments, oxygenating the substrate, changing the chemistry of the environment. Bioturbation, the churning of mud by moving organisms, transformed marine ecosystems into dynamic, layered, oxygen-rich spaces. And with each new change, a new vulnerability. A single innovation, like burrowing, could disrupt the habitats of others. A successful grazer could deplete microbial mats. A chemical shift could make old metabolic pathways obsolete. Evolution, it turns out, is not just about climbing ladders, it's also about weathering avalanches. These cascades of change are not always visible in the fossil record. Often, they leave traces only in chemical ratios, in tiny shifts in carbon or sulfur isotopes, in minerals that only form under certain biological conditions. But to those who know how to read them, they speak volumes. They tell of rising oxygen levels just before multicellular life took hold. They speak of iron disappearing from the oceans as oxygen surged. They record pulses of carbon burial, signs of massive algal blooms, global extinctions, evolutionary rebounds. Even today, the Earth's rocks carry these memories like pages of a slow-turning book, written not in words but in atoms. And every now and then the story takes a sharp turn. A sharp turn, yes, because the story of life is not linear. It doesn't move smoothly from simplicity to complexity, from problem to solution. Instead, it loops, it folds, it doubles back on itself. Each new adaptation introduces new stress. Each innovation makes room for its own undoing. When multicellular life finally took root in the late Ediacaran, the ecosystem didn't just grow more diverse, it grew more interdependent and therefore more fragile. Some organisms began modifying their environments in ways that made life easier, and sometimes, unintentionally, more precarious. Burrowing animals oxygenated the seafloor, but they also disturbed microbial mats that had anchored the ecosystem for eons. Grazers cleared swathes of bacterial communities that other species relied on. For every gain, a loss. For every breakthrough, a collapse waiting in the wings. And then, as Earth tipped into the Cambrian, came the next cascade. Roughly 541 million years ago, the fossil record explodes with forms. Hard shells, jointed limbs, compound eyes. The Cambrian explosion wasn't a singular event, but a geological moment when evolutionary pressures, chemical thresholds, and ecological complexity finally aligned. And what had once crawled now scuttled. What had once absorbed now bit. What had once grazed now hunted. Predation emerged as a dominant force, not in theory, but in armour and teeth. This changed everything. Organisms now had to evolve not just to feed, but to not be fed upon. Defensive structures hardened. Reflexes sharpened. Nervous systems grew more complex, perhaps even giving rise to the earliest glimmers of sensation, pain, pleasure, alertness. The biosphere became a battlefield, not only of matter, but of information. Those who could process the world faster had the edge. This wasn't violence for its own sake. It was selection working through feedback. Predator pushing prey, prey shaping predator, each one sculpting the other in an endless biological duet. And beneath this dance was the quiet machinery of climate and chemistry, still ticking, still steering from behind the scenes. The rising complexity of animal life increased the demand on Earth's oxygen budget. Larger organisms need more energy. And more energy meant faster metabolisms, faster breathing, more waste, more carbon cycling. Microbial processes had to keep pace. Photosynthetic plankton rose in importance, not only feeding the food web, but regulating the balance of gases in the air and sea. As these interactions layered and multiplied, ecosystems became deeper, more tangled, more sensitive. A bloom of one species could now cascade across dozens of others. A crash in oxygen levels, caused by changes in ocean currents, volcanic gas, or a decline in algal productivity, could ripple through entire habitats, and this happened many times. There were pulses of extinction during and after the Cambrian, short-lived radiations of strange, wonderful creatures that vanished just as quickly. Trilobites, once dominant, experienced multiple die-offs. Soft-bodied lineages gave way to those with armour and spines. Anomalocaridids, once top predators, faded into evolutionary memory, replaced by more efficient swimmers. In the Ordovician period, about 485 million years ago, Earth underwent another transformation. Marine life expanded dramatically. Coral-like animals built early reefs. Filter feeders like brachiopods and graptolites filled the seas. Algae carpets thickened. Life was not just surviving, it was sculpting the very shape of the sea floor. But this growth had consequences. As organisms colonized the shallows, they changed the flow of nutrients. Sediment patterns shifted. Photosynthesis altered the composition of seawater, and once again the climate began to tilt, toward cold, toward ice. Around 444 million years ago, the planet entered the late Ordovician glaciation. Driven by tectonic shifts, changes in ocean circulation, and declining CO2 levels, the Earth cooled dramatically. Glaciers expanded, sea levels fell. Shallow marine habitats, home to most life at the time, disappeared under the ice or dried out entirely. It was the second great mass extinction. More than 80% of marine species vanished. And yet, from the aftermath came new opportunity. Survivors spread into emptied niches. Evolution redrew the blueprints once again. This cycle of innovation, stress, collapse, and renewal would repeat many times over Earth's history. The Devonian, the Permian, the Triassic, the Cretaceous. Each age brought new breakthroughs. Each breakthrough carried the seeds of disruption. But all of it, every vertebrate, every leaf, every wing, can be traced back to those early chain reactions, to the invention of photosynthesis, to the quiet bloom of oxygen, to the molecular gamble of cooperation, to cells deciding blindly but persistently to grow more complex. We talk about evolution as though it's a ladder, but it's more like a branching tree, gnarled, twisting, full of dead ends and surprise offshoots. The path from protocell to planet-spanning biodiversity was never straightforward, and it was never guaranteed. The emergence of intelligence, for example, our intelligence, is a very recent thread, barely a few centimetres long on the full length of Earth's timeline. For most of the planet's history, life was simple. For most of the life's history, complexity was the outlier. But something about this planet, its chemistry, its cycles, its chaos, kept nudging life forward. Perhaps the Earth's plate tectonics, always shuffling continents and stirring nutrients, played a role. Perhaps the moon, keeping tides rhythmic and stable, offered the right kind of fluctuation. Perhaps the planet's size, large enough to retain atmosphere, small enough to avoid crushing gravity, allowed just the right balance between chance and constraint. Whatever the combination, it worked. And so, here we are. Talking about cells while made of cells, breathing oxygen because ancient microbes decided to release it as waste, living on land sculpted by algae and rain. Our bones contain calcium borrowed from ancient shells. Our blood carries iron once filtered by bacterial metabolisms. Our brains, capable of imagining the origin of life, are built by DNA forged in oceans that no longer exist. We are not outside of this chain reaction. We are one of its outcomes, and the reactions continue. Life today still rewrites the Earth. Forests draw down carbon, coral reefs shape coastlines, microbes influence cloud formation. The biosphere is not a background, it is an engine. Even now in the Anthropocene, an era shaped by human hands, the chain of cause and effect stretches unbroken. Our industries emit gases that warm the climate. Our agriculture alters the nitrogen cycle. Our cities change the albedo of the land. Our decisions are triggers now too, and the Earth responds. That response may be slow, it may be complex, but it will happen, because this planet is not a passive canvas. It listens, it absorbs, it shifts, just as it always has. From the first flicker of protocells in a shallow pool, to the rise of oxygen and the fall of glaciers, to the explosion of bodies and the retreat of trilobites, to us, watching and wondering under LED lights and digital constellations. It's all one long, delicate chain, and every link matters. In the long memory of the Earth, no event stands entirely alone. Even the most singular of moments, the first breath of oxygen, the first movement of a limb, the first bloom of a coral reef, is part of a larger pattern, a rhythm that plays out across deep time, woven from repetition, recurrence, reinvention. To understand the origin of life, truly understand it, we must look not just at its beginning, but at how it echoes through everything that came after. We must listen for themes, recurring melodies, the slow return of old motifs in new keys. Because Earth, for all its chaos, is not random. It has a kind of memory, a deep structure of cycles and feedbacks that shape the conditions for life and for death. And as life evolved, it began to interact with those cycles, to ride them, to bend them, sometimes to be broken by them. The earliest signs of this are written not in bones but in layers. Take, for instance, the carbon cycle, the great conveyor belt of life's breath. Carbon moves between air, ocean, rock and living things in a cycle that spans minutes and millennia. Plants absorb carbon dioxide during photosynthesis. Animals eat plants. Microbes break down waste. Volcanoes release carbon. Oceans absorb it. Rocks lock it away. And when this cycle is in balance, the climate is stable, the seas remain alkaline, and life flourishes. But balance is delicate. It only takes a small push, a shift in tectonics, a change in the tilt of the Earth, a surge of volcanic gas to send the cycle spiralling. And throughout Earth's history, it has spiraled many times, sometimes gently, sometimes catastrophically. One of the earliest such upheavals occurred during the Paleoproterozoic era, around 2.4 billion years ago, when oxygen first began to accumulate in the atmosphere. We call it the Great Oxygenation Event, but to many early life forms, it was a slow and poisonous catastrophe. Methane, a powerful greenhouse gas, was stripped away by rising oxygen. The Earth cooled, ice spread, anaerobic organisms, dominant until then, perished in droves. It was not the first mass extinction, but it was among the most profound. And yet, out of that collapse came something new. The survivors evolved new metabolisms. Eukaryotes appeared. The oxygen that once killed became the basis for new, powerful ways of living. We can trace similar patterns throughout the eons. Fast forward to the Cryogenian period, roughly 720 to 635 million years ago. The Snowball Earth events. Not one, but possibly two global glaciations that may have turned the planet into a near-frozen marble. The cause? Still debated. Perhaps a drop in volcanic CO2. Perhaps increased weathering from newly exposed land. Perhaps changes in the carbon cycle triggered by photosynthetic overproduction. Whatever the spark, the result was dramatic. Glaciers at the equator, ocean life retreating into thermal refuges, continents buried beneath miles of ice. And yet, again, life persisted. Microbes clustered around hydrothermal vents. Photosynthesizers may have endured in pockets of open water. The freeze may have even cleared the evolutionary stage, making way for the first animals. This pattern repeats with uncanny frequency. A disturbance in Earth's systems, volcanic, climatic, atmospheric, leads to extinction. Extinction opens ecological space. New forms evolve to fill it. It happened again at the end of the Ordovician, about 440 million years ago, when a short but intense glaciation caused sea levels to crash and reef systems to vanish. Over 80% of marine species disappeared, but from the survivors came new kinds of corals, new mollusks, new jawless fish. The Silurian period that followed was a time of recovery, but also of reimagining. Then, around 375 million years ago, in the late Devonian, came another wave of extinctions. This one was longer, more staggered, less immediately visible in the fossil record, but devastating all the same. The causes may have included volcanic eruptions, oxygen-depleted oceans, or even the rise of land plants which altered erosion and nutrient runoff. Whatever the trigger, the impact was sweeping. Reefs collapsed, armoured fish declined. The seas emptied again, but the vacuum allowed for something extraordinary: amphibians, creatures that could breathe air, that could crawl from the water and walk. Not well, not gracefully, not yet, but enough. Enough to spark a new story. The Carboniferous period that followed saw the rise of dense forests, sprawling wetlands, giant insects nourished by high oxygen, and the first reptiles laying eggs on dry land. The land, long silent, was now a stage. But the story turned again. Around 252 million years ago came the greatest of all known extinctions, the Permian Triassic event, the Great Dying. It is hard to describe the scale. More than 90% of marine species, 70% of terrestrial vertebrates, forests vanished. Insects, typically resilient, suffered massive losses. The world went quiet. The cause? A convergence of disasters. Massive volcanic eruptions in Siberia released floods of basalt and enough CO2 to warm the planet dramatically. Ocean temperatures spiked. Acidification increased. Methane was released from frozen clathrates. Anoxic conditions spread across the seafloor. The carbon cycle unravelled. For millions of years, Earth was a hostile place, and yet, once more, life returned. In the Triassic, new forms emerged, the first dinosaurs, early mammals, resilient reptiles. Evolution was cautious at first, but as the environment stabilized, it quickened. And then, at the end of the Triassic, another extinction. Then again, 66 million years ago. The most famous of them all, a rock from the sky, the Chicxulub impact, an asteroid striking the Yucatan Peninsula, releasing energy equivalent to billions of atomic bombs, fires, ash clouds, a nuclear winter, and in the months and years that followed, 75% of species gone, including most notably the non-avian dinosaurs. But in the ashes, mammals flourished, not because they were better, not because they deserved it, but because they fit what the Earth had become. This, again and again, is the broader context of life on Earth. Boom and bust, innovation and erasure. A looping, pulsing history of survival, collapse and rebirth. It's tempting to think of life as climbing a ladder, but more often it hangs on. It weathers the storm, it regrows, and these extinctions, these punctuation marks in Earth's narrative, are not always endings. Sometimes they are edits, sometimes they are necessary silences, like a forest fire that clears old growth. The mass extinctions made room. Not kindly, not cleanly, but absolutely. And perhaps the deepest lesson is this: Earth does not protect life from change. It tests it with change. No habitat is permanent. No lineage is sacred. No adaptation is ever enough forever. But from that impermanence, life draws strength. Each mass extinction prunes the tree of life, and each time it blooms again, not with the same branches, but with new ones, different, unexpected, sometimes better suited, sometimes not, but always, always alive. Always alive, yes, but not always in the same way. The forms change, the faces change, but the engine keeps turning, and it's that turning, the rhythm of crisis and renewal, that gives Earth's history its particular shape, its texture. Each extinction is not just a wipeout, it is a bottleneck, a narrowing of possibility, a resetting of the rules, and from that reset the survivors emerge into a changed world, one where old strategies may no longer work, where the air is hotter or colder, where the ocean is thicker with sulfur or newly rich with nutrients, where the sun shines through a different kind of sky. It's not just a matter of endurance, it's a matter of reinvention. The species that live after are not simply those who avoided destruction. They are those who adapted to the aftermath. This is true for the first bacteria who survived the oxygenation event by evolving antioxidant enzymes. It's true for the early mammals who crept through the darkness after the asteroid fell. It's true for every organism that learned to live not just in the world it knew, but in the world that came after. And it's here that we begin to see the true complexity of life's long story, not just as a single arc, but as a nested structure. Stories within stories, events within events, a kaleidoscope of contingency. The rise of oxygen, for example, may have been triggered in part by tectonic uplift, which exposed new minerals to weathering, which drew down carbon dioxide, which cooled the planet, which created climate stress, which changed microbial communities, which altered how oxygen was used, which increased the burial of organic carbon, which further increased oxygen in the atmosphere. Cause and effect, looping back on themselves, like a river that braids and meanders, doubling back through its own currents. Another example, the Devonian extinction. Long attributed to volcanic activity or asteroid impacts, recent theories suggest the culprit may have been plants, specifically the first forests. As vascular plants spread across land, their roots broke down rocks, altering the flow of minerals into the sea. This increased nutrient runoff, which caused algal blooms, which triggered anoxic events in the oceans, which led to marine die-offs. the greening of the continents, a beautiful slow revolution, may have led, paradoxically, to catastrophe. But then again, that catastrophe cleared the stage for the next act. It set the conditions for new ecosystems, richer soils, more stable carbon cycles, new interactions between land and life. Every step forward carries its shadow. Even the rise of complexity, something we often celebrate as inevitable progress, came at a cost. Larger, more complex organisms are more specialized, more dependent on stable conditions. They're slower to reproduce. They have more to lose. Simpler life forms, like bacteria, are far more resilient to environmental change, and they remain, quietly, stubbornly, the dominant form of life on Earth. By biomass, by genetic diversity, by sheer adaptability. We are guests in a microbial world. Even now, as we build cities and launch satellites, our bodies are still colonies, trillions of microbial cells living alongside us, inside us, helping us digest, fight disease, regulate mood. The mitochondria in our cells, once free-living bacteria, still carry their own DNA, a passport stamped with ancient visas, a reminder that even our complexity was once someone else's simplicity. The nested stories continue. In the geological record, patterns emerge. The periodicity of extinction, the ebb and flow of biodiversity. Some scientists see a cycle of roughly 26 to 30 million years, where extinction pulses align with movements of the solar system through the galactic plane, possibly increasing exposure to cosmic radiation. Others point to cycles in volcanic activity, or tectonic supercycles where continents merge into supercontinents, then break apart again, altering ocean currents, climate, and evolution. Earth breathes in rhythms far slower than ours. It dreams in million-year intervals. We're just beginning to recognize the cadence. And then there is the question of direction, of purpose. Did life evolve toward complexity, toward consciousness, toward us? Perhaps not. Complexity has increased, yes, but unevenly. Unevenly, and not universally. There are more species of bacteria now than ever. More simplicity, more redundancy, more elegance in small things. Complexity is not better. It is simply one path among many. And consciousness, for all its wonder, may be more of a side effect than a goal. An emergent property of feedback loops in brains built for survival. Still, there is beauty in emergence. From the amino acids that first formed in ancient pools, to the protocells that began copying themselves, to the ribosomes that translated code, to the multicellular alliances, to the eyes that watched the sunrise, to the minds that asked where it all came from. Each layer folded into the next. Each new stage retained a trace of the one before. The genetic code, once scribbled in random chains, became a common language across all life. The biochemical pathways developed by ancient microbes are still used today. The shape of a limb, the design of a wing, the rhythm of a heartbeat, all carry echoes of older solutions, nested stories, palimpsests of biology. To study evolution is to peel back these layers, to see not just how life has changed, but how much of it has stayed the same, and to see, perhaps most poignantly, that life is not only shaped by extinction, it is shaped by survival. Survival is quiet. It doesn't always leave fossils, it leaves lineages. It leaves mosses that have covered the same stones for 400 million years. It leaves horseshoe crabs, barely altered since the age of dinosaurs. It leaves cyanobacteria, still building stromatolites in warm, shallow seas. And it leaves us, standing here, with our brief lives and curious eyes, trying to understand a story that is older than language. In the grand cycles of Earth, we are a new melody. But we are played on ancient strings. So when we ask how life began, we must also ask, how has it lasted? How has it returned over and over from the brink? How has it woven catastrophe into creation? That is the broader context. That is the shape of life's true story. Not a climb, but a spiral. Not a victory, but a persistence. Not a single thread, but a tapestry, frayed, repaired, unfinished, and still being woven. For all the billions of years that life has pulsed across this planet, humans have only just arrived. We are new, a blink, a footnote in time. But in that blink we have turned our attention backward, eyes squinting into the darkness, hands brushing the dust from ancient stones, minds tracing patterns older than language. And it is here, in the quiet art of asking questions, that the story of life's discovery truly begins. It doesn't begin in gleaming labs or digital databases. It begins in the field, in lonely deserts and cold mountaintops, in the mud beside rivers, in the fingers of someone turning over a rock just to see what's underneath. Take a moment, picture it. A wide expanse of rock in Western Australia baked under the harsh sun. Nothing moves, nothing blooms. But underfoot, layered into the ancient crust, lie some of the oldest records of life on Earth. Here, in the Pilbara Craton, a geologist crouches, brushing away loose grit from a formation called the apex chert. It's banded, rust-red and white, compressed through time, and within it, tiny structures, so small they can barely be seen without magnification, begin to suggest something remarkable. Filaments, threads, cellular shapes. The geologist is William Schopf, and what he sees, what he believes he sees, are microfossils. 3.5 billion years old. It's not a dramatic find. There are no gasps, no gleaming bones pulled from the dirt, just rock and possibility. His discovery, published in the 1990s, was met with a mix of awe and skepticism. Could these be remnants of the earliest life? Or were they just odd mineral formations shaped by pressure and chance? Science, after all, is cautious, and the Earth does not always give up its secrets easily. But Schopf wasn't alone in the search. Thousands of miles away, in the Isua Greenstone Belt of Greenland, other scientists were scanning ancient rocks for chemical signatures, the isotopic whispers of biology. In layers over 3.8 billion years old, they found carbon ratios that hinted at metabolic processes, skewed in the way only living systems seem to skew them. It wasn't proof, but it was music in the static. And the more scientists listened, the more they began to hear. In Western Australia again, in the Shark Bay region, living stromatolites, dome-like structures built by microbial mats, were found thriving in shallow saline lagoons. Their structure mirrored those preserved in ancient rocks, not perfectly but closely enough to suggest continuity. What had once seemed foreign, alien even, now looked familiar. Life, ancient and modern, were not separated by chasms of design. They shared strategies, patterns, rhythms. And so the hunt expanded. To Canada's Nunavut Belt, where zircon crystals and iron formations may hold records from Earth's earliest ocean floors. To South Africa's Barberton greenstones, where volcanic sediments have trapped ancient bubbles of gas. To the bottom of the ocean, where hydrothermal vents belch heat and minerals into the dark, and where, in 1977, a deep-sea submersible named Alvin stumbled upon entire ecosystems living without sunlight. That discovery, led by Jack Corliss and a team of astonished oceanographers, transformed our view of what life could be. Before then, it was assumed that all ecosystems depended on the sun. But here were tube worms, clams, and microbes thriving in chemical energy, drawing sustenance from hydrogen sulfide. Life, it seemed, had more than one blueprint. It had options. And if it could begin here, in darkness, in pressure, in heat, perhaps it had begun in the same places billions of years ago. From this, a new hypothesis emerged. Maybe life didn't start in warm ponds under the sun. Maybe it started in the depths, in alkaline hydrothermal vents. Places like the Lost City, a strange carbonate-covered formation discovered in the Atlantic in 2000, where chimneys tower like castles and microbial life still thrives. At the heart of this idea was a chemist's vision, a vision advanced by scientists like Nick Lane and Michael Russell, who proposed that the natural proton gradients found in these vents could have driven the first metabolic reactions. Simple chemistry, guided by minerals and temperature, slowly tipping into biology. To explore this, researchers have tried to recreate these environments in the lab. Tiny chambers filled with iron-sulfur catalysts, controlled flows of alkaline and acidic solutions, measuring whether simple molecules, lipids, nucleotides, will assemble themselves. Some do, some don't. But with each trial, the edge of the possible grows a little wider. These are not headlines, they are quiet efforts. Years of work for a single result, months spent watching bubbles, weeks analysing molecular ratios. And yet, this is how understanding grows, not in leaps, but in layers. Consider Jack Szostak, a Nobel laureate who has spent much of his career exploring how primitive cells, protocells, could have formed. He and his team have shown that fatty acids can self-assemble into membranes, that these membranes can grow, that they can divide, that strands of RNA can be trapped within them and perhaps even replicated. They're not alive, but they're getting close. Elsewhere, researchers like Gerald Joyce have experimented with RNA molecules that can replicate themselves, imperfectly, but with variation. The basic ingredients of evolution in a test tube. Each breakthrough brings more questions. Each answer opens a dozen doors. And through it all, the people behind the science remain, not faceless, but deeply human. They hike with backpacks full of sample jars. They argue over microscope slides. They get lost in data sets. They make mistakes. They fall in love with rocks. And sometimes, just sometimes, they glimpse something extraordinary. Like Felisa Wolf-Simon, who once proposed that a bacterium in California's Mono Lake might be able to use arsenic in place of phosphorus. A bold, controversial idea that challenged long-held assumptions about life's chemistry. Her findings sparked debate, criticism, and eventually refinement. The bacteria turned out not to replace phosphorus completely, but they did push the boundaries of what biochemistry could tolerate. Science, after all, is not about being right. It's about being willing to ask, to imagine, to be wrong in useful ways. Even when we look upward, toward other worlds, we carry this spirit. The Mars rovers, spirit, opportunity, curiosity, perseverance, are not just tools of exploration. They are emissaries of our questions. Each rock they drill, each grain they analyse is part of this same pursuit, to know how life began and whether it has begun elsewhere. And behind those rovers are engineers and geologists and planetary scientists, people like Abigail Allwood, who led one of the first Martian missions with the explicit goal of looking for biosignatures in ancient rock. People like Natalie Batalha, who studies exoplanets in the habitable zones of distant stars. People like Carl Sagan, who once wrote that we're a way for the cosmos to know itself. It is a beautiful idea that the same atoms forged in stars, the same molecules that dance in ancient oceans, could eventually wonder about their own origins. But it is not an easy journey. It is built on missteps, on failed experiments, on heated debates between colleagues who see the same data from opposite directions, on the long, slow refining of theories that never quite arrive at certainty. Even the field of astrobiology, once seen as fringe, is now central to NASA's mission. Its practitioners ask, what are the universal signatures of life? What is chemistry's capacity for complexity? If life can emerge from non-life here, can it do so elsewhere? These are not idle speculations. They are grounded in geochemistry and thermodynamics, in the hard lessons of Earth's own history, and they are carried forward by people, by graduate students up to their knees in mud, pulling sediment cores from ancient lake beds, by physicists who model early Earth atmospheres on supercomputers, tuning in carbon dioxide and dialing out oxygen, by biologists who spend years studying a single enzyme, by paleontologists who chip carefully through shale, hoping to find something soft-bodied, something new. They are not all famous, most of them aren't, but they are the quiet tenders of a grand flame, the fire of curiosity. And in their hands, the story of life's origin becomes not just a question of chemistry, but of connection, a link between past and present, between the vastness of deep time and the intimacy of a single question. How did we get here? It's the question that hovers behind every rock sample, every microscope slide, every silent hike into barren lands. It lingers not in lecture halls, but in the windswept ridges of Greenland, in the searing heat of Western Australia's outback, in the muffled quiet of deep-sea submarines drifting through vents that glow like the windows of another world. And it is asked not just by specialists, but by people whose stories intertwine with the search they've chosen to follow. Consider Lynn Margulis. Her idea that the complex cells of animals and plants evolved through symbiosis, through one cell engulfing another and forming a partnership, was at first dismissed. Too strange, too messy. But she persisted, gathering evidence, making her case again and again. Eventually the scientific world caught up. Mitochondria and chloroplasts were found to have their own DNA, distinct from the host cells. They bore all the hallmarks of once independent organisms. What had seemed improbable became central, a new way of thinking, and with it, a new appreciation that cooperation, not just competition, plays a role in evolution's unfolding. Margulis didn't just alter a theory. She reshaped our view of biology itself, from a battlefield to a network. Elsewhere, in the wind-beaten cliffs of Newfoundland and the rocky beds of Namibia, scientists uncovered fossils of the Ediacaran biota, soft-bodied organisms older than the Cambrian explosion, older than skeletons, older than nervous systems. For decades their significance was unclear. Were they animals? Algae? Something else entirely? It took decades of careful analysis, of patient comparisons, of new imaging technologies and persistent questions to place them in the story of life. And even now, their exact position is debated, but their importance is not. They remind us that evolution is not always a straight line from simple to complex. Sometimes it detours, sometimes it experiments, sometimes it leaves behind a cast of characters that do not lead to us, but that matter deeply in their moment. Many of the scientists who study them never seek the spotlight. Their names rarely reach headlines, but their boots wear out from fieldwork. Their journals fill with sketches and notes. Their computers run models deep into the night. Behind every textbook diagram lies someone who spent a lifetime uncovering a single truth. Someone like Stanley Miller, who in 1953, under the guidance of Harold Urey, ran an electric spark through a flask of gases meant to resemble Earth's early atmosphere. A simple setup: water, methane, ammonia, hydrogen. Heat and sparks to mimic lightning and volcanic activity. And within days the solution turned cloudy. Organic compounds began to appear, amino acids, the building blocks of proteins. It was a moment that reshaped origin of life research, a sign that life's ingredients might not be rare, that they could form under the right conditions with no guiding hand, that maybe life is not a miracle but a property of matter given time. Miller's experiment has since been repeated and refined many times. Some versions use different gases, others add minerals, UV light, or cycles of drying and rehydration, but the core idea remains: complexity from simplicity, order from chaos, chemistry, bending toward biology. And it wasn't just in labs or rocks that discoveries unfolded. In 1984, a young geologist named Martin Brazier was mapping ancient microbial structures when he began to suspect that some of the oldest fossils might not be biological at all, that they might be pseudo-fossils, structures created by geological processes. He challenged existing interpretations, not to tear down, but to sharpen the science. It was a reminder that discovery also includes revision, that understanding is not static, that truth is often provisional, waiting to be improved by clearer eyes, newer tools. Brazier's work led others to refine their methods. to apply new techniques like synchrotron imaging, isotope geochemistry, and three-dimensional modelling. With each new advance, the old questions gained sharper focus, and the uncertainty, rather than being a flaw, became the fertile soil in which better answers could grow. And always, in the background, is the simple fact of time. The span between the formation of Earth and the appearance of humans is almost too vast to hold in the mind. But scientists have tried. They've used radiometric dating to measure the ages of rocks, zircons, meteorites. They've calibrated molecular clocks, tracing the rate of mutation in DNA to estimate when lineages split. They've modelled climates, reconstructed atmospheres, tracked the wobbles of Earth's orbit. Piece by piece, they've assembled a portrait of a world that is not static but shifting. A world that is not set apart from life, but shaped by it. These discoveries often happen slowly. Years may pass between field seasons. Funding is tight. Weather can ruin an expedition. Political borders can close. Equipment breaks. But the questions remain, and the people keep asking. Sometimes they are children poking at fossils in stream beds. Sometimes they are retirees reading about astrobiology in the evening. Sometimes they are technicians in labs, pouring samples into machines that hum quietly as they process the past. And through it all, there is a quiet sense of shared effort, that no one finds these answers alone. The geologist needs the chemist, the molecular biologist needs the paleontologist, the theorist needs the technician, the poet needs them all. Because the story of life is not only a scientific one, it is emotional, it is philosophical, it is deeply, unmistakably human. It stirs something inside us, not just curiosity, but belonging. We are made of the same atoms as the rocks we study. Our thoughts flicker in molecules first forged in stars. Our questions arise from brains built by evolution, built by cells, built by chemistry. And when we stand at the edge of a fossil bed, or run a model of early Earth, or hold a meteorite in our palm, we are touching a thread that runs backward, through ancestors, through accidents, through fire and water and stone, to the moment when life first flickered into being. We do not remember it, but we carry it, in every heartbeat, in every breath, in every spiral of DNA. That is why we study. That is why we dig. That is why we ask. Not to conquer the past, but to listen to it. And sometimes in that listening the past speaks back. A strange lipid in an ancient rock. A fossilized microbe beneath 1 billion years of pressure. A mutation shared by all life on Earth. A chemical reaction that whispers, I was here. And in those moments we are not separate from the story. We are within it. We are the newest chapter, the latest voice. Not because we are the end, but because we are still asking, still wondering, still walking through the dust of forgotten worlds, chasing echoes, and maybe, just maybe, getting closer to an answer. By now the story of life may feel like a great river, wide, ancient, full of turns, but beneath the surface there are deeper currents, invisible forces, quiet processes, and if the last chapters were about the people who searched for answers, this one is about the answers themselves, or rather, about how we come to know them. Because beneath the poetry and the fossils, beneath the field notes and the theories, lies the foundation of all understanding, science, the long, careful art of asking how. And in the story of life's beginning, science dives deep. It begins perhaps with chemistry, not in the way we learn it in school, with beakers and balanced equations, but in the raw, restless dance of molecules. At its heart, life is not magic. It is chemistry that learned to persist, to copy, to remember. And this kind of chemistry, the kind that builds itself, is rare. It requires just the right conditions. Not too hot, not too cold. Not too chaotic, not too still. Energy must flow but not overwhelm. Molecules must bump and bond but also hold together. And somewhere in that window, narrow but not impossible, the building blocks of life can form. We call this pre-biotic chemistry, and in recent decades, scientists have gone to great lengths to recreate it. In labs across the world, researchers have mixed gases, minerals and water to mimic early Earth environments. They've simulated volcanic lightning, ultraviolet radiation, hydrothermal vent gradients. And from these conditions, complex molecules have emerged. Amino acids, sugars, even nucleotides. Not yet life, but close. Still, forming the ingredients is only the beginning. The deeper question is, how do they come together? How do molecules, simple, mindless, assemble into systems that grow, divide, adapt? One line of inquiry follows lipids. Fatty acids, in the right conditions, spontaneously form spheres, bubbles with a thin membrane. These vesicles can trap other molecules inside. They can grow by absorbing more lipids. They can divide under physical stress like shaking or heating. In this way, protocells might have emerged. Not alive, but bounded. Distinct from their environment, capable of containing chemistry, and therefore of being shaped by it. Inside these bubbles, another miracle, nucleic acids. RNA, in particular, has emerged as a likely candidate for the first genetic material. Unlike DNA, RNA can both store information and catalyze reactions. It can, under certain conditions, replicate itself, imperfectly, but with variation. This idea, the RNA World Hypothesis, suggests that early life may have started not with proteins, but with RNA molecules copying themselves inside lipid bubbles. Some copies would be more stable, some faster. Natural selection, the quiet engine of evolution, would begin to turn. But RNA is delicate, it breaks down easily. Its components don't form spontaneously under all conditions. So scientists have asked, what came before? Could simpler molecules, called protonucleotides, have served as stepping stones? Could mineral surfaces have helped organize and stabilize them? Could cycles of drying and rehydration, like those in tidal pools or clay beds, have concentrated them, nudged them toward order? This is where geochemistry enters the stage, not as a background, but as a partner. Rocks, after all, are not passive. They catalyze reactions, they donate electrons, they absorb toxins. In some places, they create gradients, differences in temperature, acidity, salinity, that can drive reactions forward. At hydrothermal vents, for example, iron-sulfur minerals create sharp chemical contrasts. These gradients, combined with natural pores and surfaces, could have concentrated molecules and fed energy into early metabolism. Michael Russell and colleagues proposed that such vents were not just cradles, but reactors, places where water and rock did the first biochemistry, where CO2 and hydrogen, with the help of metal catalysts, formed organic compounds, where the first energy cycles, the precursors to metabolism, began to hum, and energy is key. Life is not just structure, it is process, a constant flow of electrons, of protons, of gradients being flattened. The earliest metabolisms likely resembled the pathways still used by some modern microbes, pathways like the Wood-Ljungdahl pathway, which fixes carbon using hydrogen gas. This process, quiet, ancient, efficient, does not require light, only chemistry, and it leaves behind chemical fingerprints, isotopes. In the rocks of early Earth, carbon exists in different forms, heavier and lighter isotopes. Biological processes tend to favour the lighter versions. When we find ancient rocks with an unusual abundance of light carbon, we see a whisper of life, not a fossil, but a shadow, a residue of metabolism. This isotopic evidence has pushed the timeline of life back farther than fossils ever could, to over 3.8 billion years, perhaps more. In the hands of geochemists, even silence speaks. And then there is paleobiology, the search for life's remains. Not just the bones and shells of animals, but the filaments of bacteria, the mats of cyanobacteria, the mineralized traces of once soft colonies. These microfossils are studied under electron microscopes, scanned by X-ray diffraction, mapped at the molecular level. Every detail matters: the curvature of a filament, the arrangement of cells, the ratio of carbon to nitrogen. And then there are biomarkers, organic molecules that persist long after the organism is gone. Certain lipids, for instance, are only produced by specific groups of archaea. When we find them in 2.7 billion-year-old rocks, we hear the voice of an ecosystem long vanished. But these voices are faint. They must be separated from noise, from contamination, from false positives, from abiotic lookalikes. That's why scientists spend months verifying a single result, why papers go through rounds of review, why claims are cautious, sometimes frustratingly so. Because the deeper the dive, the greater the care required. And when we dive into DNA itself, the depth only increases. Molecular phylogenetics, the study of evolutionary relationships through genetic sequences, has transformed our view of life's tree. Using shared genes, scientists can trace lineages back through time, estimating when groups diverged, when traits evolved, when ancient ancestors walked or swam or photosynthesized. This has revealed surprising things: that eukaryotes, cells with nuclei, likely arose from a merger between archaea and bacteria, that mitochondria and chloroplasts were once independent organisms, that fungi are closer to animals than to plants, that humans share over half their genes with fruit flies and a quarter with lettuce. The unity of life, written in code. And yet, that code is messy, mutated, rewritten, erased and copied again. Evolution, like geology, works in fragments, and here, computer modelling becomes essential. Scientists build simulations of early Earth, of its oceans, its skies, its crust. They model how gases would interact, how temperatures would shift, how molecules might behave in different conditions. They test hypotheses not just in the lab but in silico, running millions of scenarios, watching for patterns. These models are not definitive, but they are illuminating. They help us ask better questions, and in the hands of astrobiologists they extend even farther as to other worlds. What would life look like on a planet without oxygen? Could it arise in methane seas? Could sulfur or ammonia or even silicon play a role? Here, the boundaries of Earth fall away, and yet the principles remain: energy gradients, molecular stability, environmental niches. The rules of chemistry don't change from star to star, which means the search for life is also a search for generality. Are we an exception or a pattern? The answer, still forming, lies buried in data, in stone, in models and molecules. But the trend is clear. Life, given time, energy, and chemistry, seems more probable than not. Not inevitable, but possible. And in that possibility there is awe. Because if life is possible, not just here, but elsewhere, then the chemistry of existence is not an accident. It is a tendency, a leaning toward complexity, toward replication, toward memory. And memory in biology lives in code. DNA, the coiled script of life, is not just a molecule, it is a history, a palimpsest written and rewritten across eons. And in recent years, researchers have learned to read it more deeply than ever before, not just comparing living organisms, but reconstructing extinct ones. Ancient genomes can now be inferred, even sequenced, from the bones of long-dead creatures. But even more impressively, molecular biologists are building ancestral genes. Using the sequences of modern organisms, they calculate backward, tracing changes through the branches of evolution, inferring what an ancestral enzyme or protein or gene may have looked like. Then they synthesize that gene, place it in a modern microbe, and observe how it behaves. This is resurrection biology, not of dinosaurs, but of molecules, of functions, of biological decisions made billions of years ago. And it tells us something quietly profound, that life remembers. Even as it changes, it carries its history forward. There are enzymes in your body, in your cells right now, whose architecture was first shaped in a world without oxygen, in oceans where the sun barely reached, in conditions that would kill us instantly today. You are, in the most literal sense, a museum of chemical evolution, and as we learn more about this museum, we also begin to redefine what life is. In 1992, scientists discovered Nanoarchaeum equitans, a tiny microorganism that lives attached to another microbe near hydrothermal vents. Its genome is incredibly small. It cannot survive on its own. Is it fully alive, or something in between? Then came thermoplasma, which thrives in acidic hot springs. Deinococcus radiodurans, which survives radiation thousands of times more intense than what would kill a human. Halobacteria, which live in salt levels higher than seawater. Methanogens, which exhale methane instead of carbon dioxide. These extremophils are not exceptions. They are windows. They show us that life's requirements are not as narrow as we once thought, that the Goldilocks zone of habitability, not too hot, not too cold, is broader than it seems, and that the potential homes for life, on Earth and beyond, are more numerous than we imagined. This has transformed the search for life beyond our planet. Mars, with its ancient riverbeds and recurring methane plumes. Europa, the moon of Jupiter, with its subsurface ocean warmed by tidal flexing. Enceladus, spewing plumes of water and organic molecules into space. Titan, with lakes of liquid methane and a haze of hydrocarbons. Each of these places is now studied with a question that once seemed reserved for Earth alone. Could life begin here? And what would it look like? To prepare, scientists run simulations of Titan's chemistry, of Europa's pressure, of Martian soils. They test how DNA survives in space, how microbes endure desiccation, how cells respond to low gravity. And some even ask whether life already exists in these places, perhaps not as intelligent beings, but as simple, stubborn chemistry, microbial, molecular, ancient. If found, such life would be our distant cousin, not in form but in principle. And if not, if Earth remains, for now, the only world we know to host life, that rarity makes it no less scientific. It makes it sacred, and sacred things deserve understanding. Which is why the science continues, why planetary scientists model the effects of asteroid impacts on early atmospheres, why chemists track the rates of pre-biotic reactions across different mineral surfaces, why ecologists study microbial mats in hypersaline lagoons, not just to know what lives there, but how. How does life stabilize? How does it rebuild after collapse? How does it shape its environment in return? In these questions lie entire subfields. Systems biology, which looks at life not as a list of parts, but as a network, a dynamic web of feedback and adaptation. Bioinformatics, which uses computation to detect signals in vast oceans of genetic data. Evolutionary echoes hiding in the noise. Origin of life research itself now spans dozens of disciplines, from planetary geology to synthetic biology, from evolutionary theory to chemical engineering. Even artificial life, computer programs designed to evolve, mutate and adapt, offers new perspectives. Can we recreate the logic of life without carbon, without water, without DNA? And if we can, is it still life? These questions are not philosophical distractions. They are vital. Because the more we understand life's mechanisms, the more we can identify its signatures, the traces it leaves behind. On Earth, this has meant refining our toolkit. We now detect life not just through fossils, but through isotope fractionation, trace gases in sealed bubbles, molecular biomarkers in ancient shale, oxidation patterns in minerals, nested phylogenetic trees, And as our tools improve, so too does our reach. We have carbon-dated bones to within 50 years of their death. We've recovered DNA from permafrost tens of thousands of years old. We've sequenced the genomes of entire extinct ecosystems based on soil. We found traces of microbial life 2 kilometers beneath the ocean floor and beneath Antarctic lakes, and inside the walls of nuclear reactors. Life, it turns out, not only adapts, it waits, and when the conditions are right, it returns. This is perhaps the deepest scientific truth we have uncovered, that life is not a thing, but a process, a system of patterns, feedback, cycles. It is thermodynamic flow made persistent. It is entropy rearranged into order, not indefinitely, but long enough to replicate, mutate, and adapt. And in this sense, life is not opposed to physics, it is born of it. The laws of chemistry do not forbid life, they make it difficult. But difficulty is not impossibility. With time, with energy, with the right mix of molecules and chance, life emerges, and once it does, it shapes its own future. It evolves mechanisms to repair damage, to sense surroundings, to move toward food or away from danger. It learns, in chemical terms, how to persist. And that persistence creates history, the fossil record, the geochemical archive, the tree of life, and now, us. We too are a result of those mechanisms. Our neurons fire because of ion gradients. Our muscles contract through molecular motors. Our thoughts arise from cells evolved to sense and respond. And when we use those thoughts to study life, we close a loop. We become both subject and observer, both question and answer. So when we speak of deep science, of protocells and pre-biotic reactions, of vent chemistries and genetic drift, we're not moving away from wonder. We're moving toward it. Because every process we understand, every molecule we trace back through time, brings us closer, not just to an origin, but to a realization that we are part of something vast, that the story of life is still unfolding, and that the deepest science, when done with care, becomes not cold but luminous. It illuminates the quiet machinery beneath the miracle, and lets us see with clearer eyes that the miracle remains. When we think of life's beginning, we often imagine a spark, sudden, dramatic, a birth out of nothing. But what follows is quieter, slower, and in many ways more mysterious. Because survival is not just about origin, it's about recovery, about what happens after the oxygen rises, after the oceans freeze, after the skies darken, after the meteor hits. Life begins many times, in many forms, but it rebuilds even more, and recovery. Recovery takes time. The fossil record is full of absences, whole layers where once rich communities vanish. Coral reefs replaced by silence, forests replaced by charcoal, traces of diversity narrowing into thin lines. Species vanish, habitats dissolve. For a moment, Earth holds its breath, and then, almost imperceptibly, the breath returns, not as it was before, never as it was before, but as something new, something possible in the conditions left behind. The first great oxygenation, 2.4 billion years ago, wiped out much of the anaerobic life that had thrived for over 1 billion years. Oxygen was a poison then, a strange and reactive gas that broke molecules apart. But a few organisms, already equipped with defences, found a way not only to survive it, but to use it. They invented respiration, a new way of turning food into energy, far more efficient than anything that had come before. And that energy made other things possible: larger cells, internal structures, complexity. The extinction was real, but it opened a door. Hundreds of millions of years later, during the Cryogenian period, Earth froze again. Vast glaciers reached the tropics. The ocean slumbered beneath ice. It may have lasted 10 million years, perhaps more. And for those 10 million years, Life retreated. It huddled in cracks, around vents, beneath thin spots in the ice. It waited. But when the glaciers finally melted, when the sun returned and the sea stirred, evolution exploded. Animals appeared, slowly at first, soft and strange. The Ediacaran biota with their quilted bodies and fractal limbs, then later the Cambrian explosion, a sudden bloom of diversity, with creatures armoured, jointed, eyed. Why? Perhaps because the ice had cleared the stage. Perhaps because oxygen levels finally passed a threshold. Perhaps because new habitats had emerged. Shallow seas, coastlines, estuaries. Whatever the reason, the post-glacial Earth was ripe for experimentation. Every extinction leaves room. And into that room, evolution pours. After the Ordovician extinction, new types of reef builders emerged. Corals and sponges that would go on to shape marine ecosystems for millions of years. After the Devonian collapse, amphibians expanded. The land, once sparse, began to teem. After the Permian, the most brutal of all extinctions, Earth was almost empty. The biosphere had crashed. Entire clades disappeared. But in that emptiness, the seeds of the next world germinated. Archosaurs rose. Synapsids survived. The Triassic was strange, experimental, full of odd lineages and evolutionary left turns. Some would go nowhere. Others would become dinosaurs, and mammals, and birds, and flowers. After the asteroid at the end of the Cretaceous, when the sky burned and the oceans acidified, recovery again began in shadows. Ferns bloomed in the fire-blackened soil. Rodents scurried through the ruins. Insects returned to pollinate the new growth. And slowly the forests came back. A recovery takes thousands, sometimes millions of years. But it is never passive. It is a reweaving, a stitching of threads back into a broken tapestry. And what is perhaps most beautiful and haunting is that what returns is never what was lost. The trilobites do not come back. The ammonites do not return. The forests that regrow are composed of new trees. The oceans refill with new fish. Evolution never rewinds. It reimagines. Each extinction prunes the tree of life. Each recovery changes its shape. And over time, those changes accumulate. Continents drift. Mountains rise. Ocean currents shift. Climates evolve. And life, ever responding, reshapes to fit the new Earth. Even as it reshapes Earth in turn. This feedback between life and planet is one of the long-term consequences we rarely see up close, but feel everywhere. When photosynthetic microbes flooded the atmosphere with oxygen, they changed the chemistry of the entire crust. When forests spread, they increased weathering, drawing down CO2, cooling the planet. When coral reefs expanded, they altered coastal dynamics, sediment patterns, nutrient flows. Even the evolution of land plants helped sculpt rivers, stabilize soils, deepen the carbon cycle. Life is not just a passenger on Earth. It is an architect, a geochemical force. And through billions of years of interaction, Earth became something rare. A planet with an atmosphere out of equilibrium, with oceans that remain liquid, with temperatures held within a narrow range for eons. All of it shaped by feedbacks. All of it maintained by life. Even extinction plays a role. By wiping clean the slate, it resets systems that have grown fragile or overextended. It opens niches. It clears feedback loops that may have begun to destabilize. It injects novelty. It tests resilience. But recovery is not guaranteed. There have been times when it faltered, when diversity remained low for tens of millions of years, when ecosystems stayed simple, dominated by generalists, when climate stress persisted, making life's return a slow, faltering climb. After the end Permian event, for instance, complex reef systems took nearly 100 million years to fully recover. After the end Triassic, large-bodied predators took millions of years to re-establish. Recovery is not a straight line. It is not assured. but it is real, and over deep time it is relentless. This has consequences, because every recovery layers new functions onto the biosphere. Predation emerges, then camouflage, then armour, flowers evolve, then pollinators, then co-evolutionary spirals. Each wave of life builds on the last, not perfectly, not neatly, but cumulatively. And in that accumulation lies the richness of the world we know. Forests with layered canopies, oceans with food webs that reach from plankton to whales, soil filled with fungi and microbes and roots, cycling nutrients in loops so complex we still don't fully understand them. Life has become not just diverse but integrated, and that integration, that ecological interdependence, is perhaps the most remarkable consequence of life's persistence, because it means that survival is no longer individual, it is collective. Ecosystems are networks, and in those networks, fragility and resilience intertwine. When a keystone species disappears, an entire food web can tremble. When a pollinator declines, entire plant communities feel it. But networks also buffer shocks. They spread risk, they adapt, and when given time, they rebuild. This is the quiet miracle of recovery. Not just that life returns, but that it returns complex, that it reestablishes balance, that it layers itself into a living system capable of shaping its own climate, its own soils, even its own evolutionary trajectory. And all of this began with simple chemistry, with molecules bumping in warm pools, with lipid bubbles trapping nucleotides, with sunlight splitting water. Billions of years later, that chemistry walks on two legs. It types into a keyboard, it maps genomes, it contemplates its own origins. We are the long consequence of recovery. We are the result of a world that, again and again, has picked itself up. Not because of design, not because of destiny, but because of possibility. Given time, given chance, given space, life returns. It fills the cracks, it innovates, it builds. And then, in a quiet moment, it asks, how did this happen? The answer is never simple, but it always begins the same way, with recovery, with the return of breath, with the long, slow turning of a planet, and the life that learned, again and again, how to begin. It's easy to think of deep time as distant, a vast unreachable era that belongs to rocks and microbes, not to us. The Hadean, the Archean, the Proterozoic, epochs whispered in textbooks, recited in documentaries, but always somehow separate. But the truth is quieter, more intimate. We live in deep time. We are its continuation, its voice, its result. Every breath you take is filtered through an atmosphere built by life. Every meal you eat is drawn from a food web whose roots stretch back to forgotten forests and vanished oceans. Every cell in your body hums with processes first perfected by ancient bacteria. You are not on Earth. You are of it. The hydrogen in your blood was born in the Big Bang. The calcium in your bones was forged in the cores of dying stars. The iron that carries oxygen through your body was once part of supernovae. And yet, you're not just matter, you are memory, inherited structure. The latest note in a long and patient song. This is what Earth teaches us, not in shouts but in layers, in slow sediment, in ancient ice, in the coiled strands of DNA passed down through time. And as we look back on that story, on all the crashes and comebacks, the near-deaths and renewals, we find a strange reflection of ourselves. Because now, for the first time, one species has become aware of the system it lives in. We know about extinctions not because we read about them in myths, but because we found their traces in rock. We know about past climates not from speculation, but from isotopes frozen in ice cores. We know how life began not through legend, but through experiment. And we know now how it might end, or change, or break. This is not a new extinction event, not yet, but it is a rapid one, In the last century, species have vanished faster than at any point since the dinosaurs were wiped out. Rainforests cleared, reefs bleached, oceans warmed. The climate, once regulated by slow geochemical feedbacks, is now tilting on human timescales. We've increased CO2 faster than any natural process ever did. We've moved nitrogen and phosphorus through landscapes at orders of magnitude beyond natural cycles. We've introduced plastics, pollutants, radiation, materials life never encountered before. We've become a geological force, and the planet is responding. But the lesson of Earth's history is not one of despair. It's one of scale, of rhythm, of recovery. Extinctions have happened before. Climate has shifted before. Life has teetered on the edge more than once. What's different now is not the crisis. It's the awareness. The asteroid did not know it was ending a world. The volcanoes of Siberia did not weep for the trilobites. The cyanobacteria that filled the sky with oxygen had no plan for what came next. But we can see it. We know what we're doing, and because we know, we can choose. This is where science meets responsibility, where data becomes ethics, where understanding becomes action. Because Earth will go on. It always has. It will adjust to new conditions. Oceans may rise, ecosystems may collapse, but over time, perhaps millions of years, life will reassert itself. It may be simpler, it may be stranger, it may not include us, but it will be life. The question is not whether Earth will survive. The question is whether we will survive with it. Whether the networks we rely on, for food, for air, for water, will remain intact. Whether the biodiversity that makes this planet vibrant will continue to weave its silent threads around us. Whether the stories we have inherited can be passed on. We stand at the edge of a cliff, but also at a crossroads, because the same minds that split the atom can rebuild ecosystems. The same tools that monitor climate can restore forests. The same curiosity that led us to question our origins can guide us toward new ways of living. The challenge is not technical, it is emotional, cultural, philosophical. Can we act on timescales longer than a single election? Can we value systems we don't see? Can we protect what we'll never personally benefit from? Deep Time asks us to stretch, to see ourselves not as isolated but nested, to recognize that the roots of a tree matter as much as its fruit, to realize that being modern is not about breaking free from nature, but remembering we never did. Because the bacteria in our gut still follow ancient rules, because the crops in our fields still need pollinators, because the climate around us still follows cycles older than civilization. We're a new branch on an old tree, and that tree, the tree of life, has bent, burned, and blossomed again and again. We are lucky to be living in its current bloom, lucky to have languages and music and microscopes, lucky to gaze up at the stars and ask what might live out there, lucky to breathe air enriched by eons of algae, lucky even now. And this is where philosophy returns, because science tells us what happened, but reflection asks what it means. Is life rare? Is intelligence fragile? Is consciousness a fluke? We don't know. But what we do know is this. Life on Earth has survived 4 billion years of catastrophe, change, and chaos. And every moment of beauty you've ever experienced, every bird song, every mountain dawn, every moment of laughter or awe, has been made possible by that endurance, by that long, slow resilience, by recovery. And perhaps the best way to honour that legacy is to extend it, to become part of the recovery, not the collapse, to step into the lineage not just as heirs but as caretakers. Because if we can do that, if we can learn from Earth not just as a place, but as a teacher, then maybe we can write a new kind of chapter. One where knowledge becomes compassion, one where science becomes stewardship, one where curiosity becomes care. And in that, there is hope. Because the past shows us how bad things can get, but it also shows us that from every ending something has returned. Life does not cling to a single form. It spreads, it adapts, it reinvents itself. And if we listen closely, it speaks. In the whisper of leaves, in the glow of plankton, in the pulse of your own heartbeat, it says, you are part of this, not separate, not above, part of. And once you feel that, truly feel it, the world changes. Not just in your mind, but in your breath, in your decisions, in your attention. You notice the quiet. You value the moss. You think in longer arcs. You plant trees whose shade you may never sit beneath. You act not out of fear, but out of love. And that too is evolution. A shift in behaviour, a new survival strategy. One shaped not by natural selection, but by reflection. And maybe, just maybe, it's what life has been evolving toward all along. Not intelligence, not technology, but awareness of self, of system, of story. Because when you know the story, you tend to it differently. You see that it matters, and you want it to continue, even if you'll never see how it ends. And so here we are, not at the end of the story, but at the edge of it. A pause, a quiet breath between all that has come before and all that may still come after. Tonight, we've wandered through time, from the first flickers of life in a molten sea to the rise and fall of ancient ecosystems, to the fingertips of those who still study fossils, genes and chemical traces with soft eyes and steady hands. We've drifted through oceans that no longer exist, stood beside volcanoes long since cooled, and listened to the murmur of molecules finding each other in the dark. And maybe, just maybe, we've seen ourselves a little more clearly, not as separate from the Earth, but as part of its long, patient rhythm. Life didn't arrive all at once. It gathered, it stumbled, it survived, and every step, every turn led to this moment, to you, sitting here, listening, wondering. If this brought you a little peace, a little perspective, a little something to carry into sleep, I'm grateful. And if you'd like to help this quiet corner grow, you can leave a like, subscribe, or share it with someone else who might find comfort in the questions. And I'd love to hear from you too. What's your favourite theory of life's beginning? Do you think we'll ever find life elsewhere? What's the oldest living thing you've ever seen? Leave a thought in the comments. Something small, something strange, something still unproven. Because wonder doesn't end when the episode does. It lingers. It asks softly, just as you're drifting off. What else is out there? And so, wherever you are, city or forest, desert or snow, under stars or under blankets, I hope you're feeling just a little more connected to this strange, spinning planet